Hello, making a first attempt here at recording with the OBS studio on my new computer and using a whiteboard, even though it's in vertical mode and I look kind of drunk writing on it. I'm going to try it. And as long as I'm trying all this recording stuff, let me give you a little more help understanding the Latin square model, I hope. So I hope you'll recall Latin square. P by P means I have P treatments, means I have P block factor 1, which we'll call rho, 1 blocking factor. And I actually have a second blocking factor 2, which we'll put in columns. Try again, reload. What the heck is that all about? I love Microsoft. Okay. P by P Latin square. Remember that our model is Yijk is equal to mu plus alpha I plus tau j plus beta k plus some random error term for each data point, epsilon ijk. So any given data point can be modeled as the mean of all of the data plus the effect due to its row, its treatment, its column, and its individual random error term. So just remember, this is I stands for the row, J stands for the treatment, and K stands for the column. At least I hope it's that way. I didn't go back and look at the book. But that's what I think it is. If it's not, you can just simply transpose the notation. It doesn't change the concept here. So what I'm going to do to help us understand the model better is generate some data and kind of analyze it and play with the terms and look at what happens. Just conceptually, make sure you understand that all these times we're simulating data, it's because we don't have a simple physical experiment to go out and set it up and take 16 data points and get real data. So we're doing things essentially backwards. We're taking the model and we're analyzing it, even though we already had the model and knew what the model was. In reality, you wouldn't know what the model was, or you wouldn't bother doing the experiment. So in the physical world, you would take the data having absolutely no idea what mu, alpha, tau, and beta are, and you would calculate them. But since we can't do an easy physical experiment, I'm going to do it backwards. I'm going to simulate data. If you look at the textbook, you can see that there's only p minus 2 times p minus 1 error degrees of freedom, which means in case of a 4x4, which is what we're going to do, you really only have 2 times 3 or 6 error degrees of freedom, meaning 6 independent residuals. 10 out of the 16 can be determined from the fact that the sum across any row has to be 0. The sum across any treatment has to be 0. Sum across any column has to be 0. And the sum across all of them has to be 0. So if you do the math, p squared minus 1 minus those others, you get p squared minus 3p plus 3, which it factors to p minus 2 times p minus 1, which is the error degrees of freedom. So I've taken some time before this video to take 6 random error terms independent from Minitab, just random with mean 0, standard deviation 1. I've taken the 16 combinations, and in yellow I've blocked out the ones that essentially can be computed by the fact that sum across any row has to be 0, sum across any column has to be 0, sum across any treatment has to be 0. So I now have generated 16 error terms that actually meet that condition. I used the solver to set up the sum of rows, sum of columns, sum of treatments, and total mu is 0. Told it to vary the yellow ones, the 10 not independent ones, and came up with these. So I take these error terms to Minitab, paste that here. You can use any mu you want. I guess I didn't put a column in my Minitab here for mu. But I do have the 4x4 here set up already, just to save time. Rows 1 to 4, columns 1 to 4, and then treatment A, B, C, D, with any one row and any one column having only one of each letter. Any one row has only one A, B, C, D, etc. Any one column has only one A, B, C, D, etc. to satisfy the orthogonality requirement for your Latin square. I can put a column here for mu. So insert a column for mu. And let's just take it to be 50, whatever. So one more, and then I'll copy that twice or 3 more times. So the mean is always 50. Whatever number, it doesn't really matter. So let's choose some alpha effects. So what I want to do is I want to set up alpha and beta to be important here. Pretend they do, in fact, cause a lot of variation, bigger than even the treatment. So that if I didn't block by alpha and beta, I would never detect the treatment effect. It would get lost in the noise due to those 2 blocking factors. So let's keep things simple. Let's say alpha 1 is 10, 10, 10, 10. That would be row 1. And in order to get the summation 0, I'll just pick a different one. Let's pick 3. So I'll make 2, 0. Let's make 3 cancel out number 1, negative 10, negative 10, negative 10, negative 10, whoops, negative 10, and 4, 0. So I'm just picking numbers that happen to satisfy summation of tals equals 0, so it doesn't corrupt the mean. Alpha. This is the row block effect. I'm going to do something similar for beta. I'll just make it a little bit smaller. I'll make the first one 0. I'll make the second one 8. I'll make the third one 0. And then just make sure the sum is, oh, shoot, these don't go in that order. They go 1, 2, 3, 4, 1, 2, 3, 4. Sorry, I'm spacing out. So they go 1, 2, 3, 4. Let's go 0, 0, negative 8, 8. And then that pattern repeats. So I'll just copy those 3 more times. Simple, stupid mistake, right? Just going too fast. Make sure you watch where the numbers actually line up. 0, 0, negative 8, 8. 0, 0, negative 8, 8. And it pushes that down for some reason. Clear cells. Okay. So now the treatment effects. I'm going to make it smaller than, 0 and negative 8, so that it'll be clear that had we not blocked by those 2 blocking factors, we would have lost the effect of the treatment. It would have been lost in the noise. So let me just try 2 for A. So I'm going to put a 2 everywhere I have an A. And I'm going to put a 0 every place I have a B and a C. And then I'm going to balance that out with a negative 2 every place I have a D. So hopefully I'm doing this right. There's 4 spots with a D. Okay, so again, obviously I'm fudging this. We now are pretending we knew we had a mean of mu. We had 2 rows that were important, row 1 and row 3, plus and minus 10 effect. Treatment 1 gives you 2 improvement. Treatment 4 gives you a negative 2 down in the response. Beta, similar thing, except now it's column 3 and column 4, negative 8, 8. So we can just use the calculator here to calculate what our data would look like if this were our model. And I think I already have it in here. Mean plus alpha plus tau plus beta plus error. Okay, apparently I named something different. Oh, mean is not mean. Here it's mu. So instead of mean, it's mu. That should work. Alpha, tau, beta, error look like what I named everything else. So there's our simulated data, right? It's as if you had gone out having no idea what you were going to get. You set your blocking factor 1 to 1, your column 1 to 1, and your treatment to A, and you measure a data point and you write 61.8353. Then this is in random order, so maybe the next thing you did was row 3, column 3, treatment A, bang, 3324. Then maybe the next one you got was 43B, and you measured 40.67 or 6273. Eventually you get all 16 data points. The only time you go out of random order is if one of the blocking factors happen to be temporal, like day or week or month. Then of course you do those first. But assuming you can randomize across all of them, that's what you should do. And so now I'm going to analyze stat ANOVA general linear model. And the response is Y. tau, alpha, and beta, or sorry, those aren't the factors, those are the terms. The factors are, I put treatment first, and then I'll put row and column. Those are the actual factors. You don't put the coefficients in there, you wouldn't know what those are, right? So you put treatment, row, column. Model will not have the interactions, which is what we want. For results, I prefer the expanded tables and the full set. It's already set that way. So if you analyze, my treatment was not quite big enough to pick up, even though I had a lot of help from the row and column blocking factors. You'll see it's 0.166. So my treatment of 2 and negative 2 was not big enough to detect. And by the way, you're seeing those coefficients that I made up reoccur here in the analysis to prove that I did it right. With a mean of 50 here, the constant. So there's a couple ways I could make that p-value a little bigger to say, yeah, in fact, I'm confident I have a effect due to treatment. I could either reduce the random error, for example, divide this by 3 or 2 or whatever, or go generate new random error with less than 1 standard deviation. So I could do that, or I could just increase the tau effect. So I'm going to do the latter. I'm just going to add a little more to tau here. So we come back and increase beta, sorry, tau, not beta, 3 and negative 3. I'll just up it a little bit and see what we get. Whoa. Negative 3, 3, negative 3, 3, negative 3, 3. I have a feeling I just messed that up. Pattern isn't looking right. Maybe it's fine. A is 3. D is negative 3. Yeah, I messed it up somewhere. I think I overwrote a 0 there. Let me see if I have it right now. Let's make sure I have it right, because I think I fat-fingered something typing that. All right, so every place I have an A, I should have a 3. 3 is A, 3 is A, 3 is A. Good. Every place I have a B or a C, I should have 0. BC is 0, BC is 0, C is 0, B is 0, B and C are 0. Every place I have a D, I should have a negative 3. So I think it looks okay. So I've just increased the size of the treatment effect to try to get a more significant value here in the analysis. And it worked. So I have roughly 4%, 038. So your conclusion here to your boss should be you're 96.2% sure the treatments are not all the same. You might also tell the boss it's a really good thing, even though we didn't specifically test hypotheses on row and column, you could just look at this and see 800 and 512 are huge sources of random variation, or non-random variation, sources by block. Had we ignored the block, they become random, and they would dwarf that 72. So you could say, yeah, boss, it was a lot of work setting up those 2 blocking factors, but it looks like we were smart in doing so, so that became 038. Clearly, if I just ignore those 2 blocking factors, we will not detect a difference. You're not going to say, yeah, I reject a null hypothesis with 88% chance I made a mistake, right? I hope you wouldn't say that. So you would not reject a null hypothesis, and you would tell the boss, hey, treatment didn't look like it mattered, but the reality is you're wrong. The reality is there were 2 blocking factors that caused so much variation that you missed the effective treatment. Similarly, had you only blocked by one of them, treatment and row, for example, I think it'll still be problematic. So this would be as if it were a randomized block design. We still fail to reject treatment. Okay, so in this case, you would have had to block by both, such as we had before. Treatment, row, and column. And in fact, we're back to that 038. Okay, now, if, let's just say, column didn't really matter so much, we would have thrown away 3 degrees of freedom without gaining a reduction, significant reduction in the error sum of squares here, or in the sum of squares, which ultimately gets lumped to error if you don't account for it. So let's say column didn't really matter. Watch what happens here. So if I come over here and the column effect was, column effect was, let's see, beta. So let's say I just made them all 0. Get rid of them. You could just make them really small as well, but let's just make it as small as it gets. It doesn't matter at all. Okay? So if you do that, what's going to happen, what should happen, is we're going to waste the error degrees of freedom of beta here. We're not going to reduce the sum of squares at all. It's going to be 0. In reality, it would be some small number if you put realistic, very small betas in there. But we're going to see we don't actually reduce the error sum of squares at all. We throw away 3 degrees of freedom, and we're going to be less than 96.2% sure. So that was not a good design. So had you run this as a Latin square, we are, oh, sorry. Yeah, no, that's right. I expected the 038 to change when mean square error. Oh, yeah, no. The 038 is the same regardless. The point is, it would go up had we not wasted that 3 degrees of freedom. So I think I got a little circular in my logic of where I was. It doesn't really matter what that was, as long as I account for it and remove any variability due to it, I'll end up at 038. If it in fact was 0, I've wasted this 3 degrees of freedom. So I shouldn't have blocked by this. I should have, in fact, done a randomized block with only one blocking factor for rho. These 3 degrees of freedom there will then jump down to error with 9, and this 038 will actually get smaller. You'll be more confident. So we get rid of the column effect since it didn't actually matter. Again, you wouldn't know that unless you went ahead. That 038 went to 006. So in this particular case, it would have been really smart to only run a randomized block if in fact this column factor didn't cause significant variation. Okay? So I hope that helps you understand the model better. I hope that helps you understand how to generate valid data. And by the way, it should be valid data. If I go back and analyze it as a Latin square and make some residual graphs, normal versus fits, we don't know the order, but we can go versus row versus column. Fits is essentially versus treatment already, because it's fit by treatment. So should get roughly linear normal probability plot like that, and you should see no obvious trend or patterns in these other graphs. Okay, so when you do your homework 4, make sure you make this graph. If this graph doesn't look acceptably linear, if it's clearly not a line, or if there's clearly any pattern to these, not just a random mix, then you probably don't have random error that meets the assumptions. Okay, so hopefully that helps, and this was hopefully a good test of OBS Studio installed on my new computer, camera set up right, I hope, and all of that good stuff. All right, happy viewing.